Last topic, let's take a brief look at what's called molecular collisions. You know the molecules, even an ideal gas, will have to collide with each other. The distance between neighboring collisions, between successive collisions, may vary from, for example, look at this red molecule. It moves this far to hit another molecule and move a little shorter to hit the next one, and then travel another distance, and so on. The distance it travels between neighboring collisions can be long, can be short. What we want to know, actually several things we want to know. We want to know, on average, how far does the molecule have to travel before it hits another molecule? We also want to know how many collisions does a typical molecule encounter per unit time, say per second. Those are the things we want to discuss. Okay, for simplicity, let's first imagine that we freeze all other molecules, only allow one molecule to move. Okay, we're going to correct that a little later, but let's suppose we can do that. So this molecule, this red molecule, is the only one that moves. Everything else is frozen. This molecule, as it collides with other molecules, of course, whether it's going to collide with other molecules depends on its size, depends on the size of other molecules. Imagine if they're all point particles with no size whatsoever. They're never going to hit each other, right? So let's suppose, for simplicity, every molecule has the same radius r or diameter d. Okay, so this molecule comes in and strike other molecules. Remember, the other molecules do not move. We pretend they do not move. This is the path of the center of this red molecule. It moves with a speed v going this way. If another molecule, another waiting molecule is that far from the path, then as this molecule scans over, it's going to cut this path, right? It's never going to strike that molecule. Okay, here I drew another case when a waiting molecule is barely able to scrape this red molecule, right? So they hit each other, just barely hit each other at that point. Where is the center of that other molecule? Well, this is radius r, this another radius r, so the center to center separation is a distance d, which is the diameter of each molecule. So you see, for another molecule to be in the path of collision with this red molecule, the center to center separation cannot be more than d, okay, the diameter of the molecule, which means as this molecule passes through, imagine there's a cylinder of radius d, okay, d being the diameter of each molecule. Other molecules will have to, the center of other molecules must be within this cylinder in order to be in the path of this molecule, in order to have a collision with this molecule. Okay, now look at a time interval dt. During the time interval dt, this molecule moves forward by a distance of v dt, right? How many molecules does it hit? Well, that depends on how many molecules will reside in such a cylinder. Because remember, the other molecules, the center of these other molecules must be in this cylinder of radius d, right? And this is v dt. So we're looking at such a volume. Any molecule whose center is within this cylinder will be hit by this red molecule. So how many molecules do we have within the cylinder? Well, let's say if the number of molecules per unit volume is m, okay? Then all we have to do is multiply n by the volume of the cylinder, right? Then we get a total number of molecules waiting in this cylinder, and each of these molecules will be hit by this red molecule. Okay, so what's the volume? That is height times bottom area. Height is v dt. Bottom area is pi d squared. This is the number of molecules waiting in a cylinder, and each of them will have a collision with the red molecule. So this really is the n, the number of collisions suffered by this molecule as it moves with the speed v over time dt. So I want to know two things. One is, how far does this molecule travel before hitting another molecule on average? Well, it moves a distance v dt, okay? It moves a distance v dt. During that time, it suffers dn. That's the number of collisions. So how far does it have to travel for one collision? That will be this total distance traveled divided by the number of collisions it encounters, right? So v dt divided by dn, and what is that equal to? If you work it out, you find this 1 over n pi d squared. Now, we have here made an assumption, and that is the other molecules do not move. This red molecule is the only one that moves. Of course, that is not quite the correct assumption. What we really should do is to look at the relative speed between molecules. because when we say this molecule does not move, this molecule is the only one that moves, the other ones do not. Basically, what we're doing is we're looking at the relative velocity between molecules. We say, okay, relative to other molecules, how fast does this one move? That is the velocity we should be looking for. So we should be looking for relative velocity. Now, relative velocity is not the same as the velocity of individual molecules. It turns out you can do this calculation. On average, the relative speed between two molecules is square root of 2 times the speed of that molecule, the average speed. So there is a square root of 2 somewhere here. So because basically this is saying that the molecule actually moves a little faster than you expect due to the relative motion, and that shortens the average distance this molecule have to travel before it collides with another molecule. Okay, so with this correction factor, what we get here is the average distance the molecule travels before going through another collision. We give this a name, we call it L, which is the so-called mean free path. Okay, mean free path. The mean free path depends on several things. Depends on how dense the molecules are packed, of course. The denser, then the shorter the mean free path. It also depends on the size of each molecule, the diameter of each molecule. The bigger the molecules, the more likely you're going to hit each other, therefore the shorter the mean free path. If you look at some typical numbers, for example, example 6 on page 659, they use air as an example. The diameter of air molecule is, they use nitrogen to replace air because nitrogen is the most abundant air molecule. It's 2 times 10 to the negative 10 meters, and the number density n, which is the total number of air molecules divided by the volume, we can calculate it to be about 2.5 times 10 to the 25 molecules per meter cubed. If you did this calculation, you'll find that L is around 2.25 to 10 to the negative 3. Okay, so L for air at room temperature is around 2 times 10 to the negative 7 meters. Negative 7 meters. Now you compare this with the size of each molecule. Remember, the diameter of each molecule is 2 times 10 to the negative 10. Okay. So what did that tell you? L over D is about 1,000. So on average, a molecule have to travel 1,000 times at its own size before making another collision. So in this sense, we say air is actually pretty dilute as a gas. Therefore, it's not quite a surprise thing to realize that air behaves very close to an ideal gas, because after all, the air molecules are fairly dilute. The important quantity is so-called frequency of collision, and that is, on average, how many times does a typical molecule collide with other molecules per unit time? Okay, so let's look at per unit time. Per unit time, this molecule moving at average speed v bar would travel how far? Would travel v bar times 1 unit of time. That's just v bar, right? Okay, this is the total distance it travels. Now, every time it travels an extra distance of L, on average, it goes through another collision, right? So you take the total distance traveled, divided by the distance it has to travel before giving another collision. That will give you the number of collisions per unit time, doesn't it? Okay, now we can do some numerical calculation. Again, using air as an example, nitrogen molecules. The typical speed is 473 meters per second, given room temperature, 473 meters per second. That's from the same sample problem, number 6. And you divide this by the mean free path, which we already calculated, 2.25 times 10 to the negative 7 meters. This gives you the number of collisions per second for one nitrogen molecule, and that's equal to 2.10 times 10 to the 9 collisions per second. Look at that. This is 2.1 billion collisions per second. So each molecule will have to collide more than 2 billion times with other molecules per second. This tells you how frequent the collision is, and tells you, there's an efficient way for energy to be propagated by molecular collision, because the collisions happens very, very quickly.